All right. Good evening, everyone. Now, let's move to a very important topic, which is somehow different from what you have learned. So far, we have been focusing on physical chemical treatment, right? So we are utilizing physical chemical methods for water treatment, right? To remove suspended solids and other kind of substances from water, right? So starting from very beginning, we have coagulation, flocculation, right? And then sedimentation driven by gravity, right? And then sand filtration, membrane separation, right? And disinfection. So these are physical or chemical methods, right? Physical chemical methods. And here for wastewater treatment, the most distinctive feature is biological treatment, right? So now here we are utilizing the power of microorganisms. This is very different from water treatment. So in water treatment, we have not talked about biological treatment, right? But in some cases, we have microorganisms growing in the sand filter. Okay, in sand filter, we have certain microbial community and perform certain function to remove organics. Okay, for example, trace organics. Right. But here in wastewater treatment, okay, the major function is performed by microorganisms. Major removal. What's the difference between water and wastewater? What's the difference? Concentration, right? Concentration of organics, COD, BOD, a few hundred milligram per liter. That's very typical for municipal wastewater, right? Municipal wastewater. And sufficient organics, right? Sufficient organics. And here we can use microorganisms. Right? On one hand, organics can be consumed by microorganisms, right? But there needs to be sufficient organics. Otherwise, microorganisms could not sustain their growth. So we probably see more often use of biological treatment in wastewater. For even higher concentration wastewater, like industrial wastewater, COD could reach a few thousand, even more than 10,000 milligram per liter, right? So what do we do? We could use physical method, or physical chemical. We could burn it, right? Combustion, very high concentration. We could also use biological treatment, okay? But there we are utilizing anaerobic treatment, okay? So here we are mostly talking about municipal wastewater, okay? So it's aerobic with oxygen, right? Aerobic versus anaerobic. Aerobic with oxygen, right? Anaerobic without oxygen. Right. And also I want to mention for wastewater, it is still similar to water treatment. We have a process train, right? What does process train means? Multiple steps, right? Multiple steps. But here we will not talk about sedimentation again, okay? Like primary clarifier, secondary clarifier. The fundamental principle is the same as we use in water treatment. So our focus in wastewater treatment will be biological treatment, okay? Biological treatment. You need to read wastewater engineering, okay? So this is the other book, very thick, okay? The other book, chapter 2, section 9, and chapter 7 and 8, okay? All these chapters. So I'll briefly go through biology, microbiology, but we are not a microbiology class, so we'll just learn some basics relevant to our wastewater treatment. Microorganisms are everywhere, okay? Everywhere. In the coffee you drink, in the air we breathe, right? In the water we drink. It's a matter of concentration, it's a matter of types, different types, but it's abundant, okay? The number of bacteria, or more extent, microorganisms is much larger than human population on Earth, okay? So it's everywhere, and its typical feature, 1 to 10 micrometer, right? 1 to 10 micrometer. So based on the size, what method we can use to remove them from water? Can we use sedimentation? Probably difficult without coagulation, right? Unless you use some coagulant. What else? Can we use filtration? Right? So we can use filtration based on size. And it's visible under microscope, and this shows you it's everywhere. Okay? Based on its size, they can be suspended in air. Where can we find bacteria, air, water? Right? Surface water, 1 million cells per milliliter. 1 million. Huge number, right? The soils, 40 million cells per gram soil. That's extraordinary number, even under certain extreme conditions. We can also find the bacteria. Right? So total number, 5 times 10 to the 30th. Right? Human being, 8 billion. Right? We have different types of microorganisms, and we are utilizing the different types of microorganisms in wastewater treatment. Based on nutrients, where their nutrients come from. We have autotrophic and heterotrophic microorganisms. Autotrophic, they consume inorganic carbon. Right? Inorganic, CO2 and bicarbonate, right? CO2, bicarbonate. That is the source of carbon. Heterotrophic, hetero means from other sources, right? Hetero organic compounds. right? Organic compounds. In our wastewater, we're utilizing heterotrophic, right? So what are the organics? COD, BOD, right? COD, BOD. Basically, wastewater organics are the food of these microorganisms. They're carbon source. Okay, they're carbon source. So heterotrophic energy requirement, it could come from the light, that is phototroph, or from chemicals, right? Chemicals, chemotrophs, chemotrophs. And also based on the temperature range, they prefer. We have three ranges: psychrophilic organisms whose growth is optimum within 15 to 30 degrees Celsius, right? So actually low temperature, and mesophilic 30 to 45, and then thermophilic 45 to 70, right? So what does philic mean? Philic. What does philic mean? Like, right? For example, thermophilic. Philic. Philic means like, right? So the like temperature. What do we have learned? Hydrophilic. Hydrophilic. What does hydrophilic mean? What is hydro? Water, right? So they like water. Hydrophilic, right? What's the opposite? Phobic, right? Phobic, dislike. Hydrophobic. So they do not like water. They partition into the organic phase instead of water phase. So three ranges, right? And this one is important: oxygen requirement, right? Some microorganisms grow with oxygen, right? But for some, oxygen inhibit the growth, right? So we have aerobic organisms that use molecular oxygen as electron acceptor. Okay, what is electron acceptor? What is electron acceptor? Okay, this is a very important concept. Here we have electron. We have electron acceptor. On the other side, we have electron donor, right? Electron donor, electron acceptor. What is the difference? Electron donor, donation, giving out, right? Giving out. Acceptor, accept electrons. So based on the concept of redox reactions, what is that? The oxygen is an electron acceptor. What do we get? If you have oxygen, it accepts electron. What do you get? What do you get? What do you get? What do you drink? What do you drink? You get water. Right, so it's reduction. Right? So one chemical gets electron. It's a reduction reaction. So this is oxidation state of 0 to oxidation state of -2. -2. So it gets 2 electrons. All right. So what is the electron donor in our wastewater treatment? What is the electron donor? I don't have the. In wastewater, what do we have? What do we want to remove? COD, right? So what is COD? Organics, right? Organics. So organics giving out electron. What do we get? CO2. Yes. So we get CO2. This is the product. So what happens in wastewater treatment? Wastewater organics are converted into CO2, and you need oxygen to accept the electrons. So this is oxidation reaction, and that is reduction reaction. Right? So you need oxidation as well as reduction. Right? You have wastewater organics, you have oxygen, the product is CO2 and water. But that reaction happens with the help of microorganisms, right? With the help of microorganisms. And that is what happens in wastewater treatment, in biological wastewater treatment. So aerobic organisms that utilize molecular oxygen here as electron acceptors. Okay? So this is what we utilize in biological wastewater treatment to remove COD. Remove COD. Anaerobic organisms that utilize some molecules other than molecular oxygen. Okay. In our coming lecture, we'll discuss this. Okay, anaerobic in anaerobic treatment. But we'll first talk about aerobic treatment with oxygen. And facultative organism can use either oxygen or other electron acceptors. It depends on the environment. Okay, if you have oxygen, they prefer to utilize oxygen. But if you do not have oxygen there, they can utilize other electron acceptors. Right? So they are more adaptable. Right, bacterial growth. We need to provide certain condition for them to grow. What are they? Electron acceptor. Oxygen, right? We need oxygen. Nutrients, carbon, right? Carbon. Wastewater organics, right? So actually, if you have low concentration of carbon, low concentration of organics in wastewater, that is a problem for wastewater treatment plant, right? Because you are not supplying sufficient food for these microorganisms. They will starve, right? So the optimal condition is a stable supply of wastewater organics, right? So you do not want very fluctuating concentration. But in design, we have this kind of buffer tank, right? And micronutrients, some trace metals and vitamins, right? But for these nutrients, not a very high concentration. Too high is toxic, right? So there's an optimal range. And environment, moisture, temperature, and pH. Right? Temperature is important. for example, anaerobic treatment, right? These microorganisms prefer high temperature, so they are thermophilic. And what we need to do, we need to heat the reactor. Okay. Uh, this is an interesting video, right? So we see that wastewater we utilize biological treatment, right? So what are the microorganisms we utilize? These are the microorganisms. We can see a lot of different types. And for different wastewater, with different wastewater treatment plants, you could have different dominant species. And you can actually judge the treatment efficiency, effluent quality, etc., from these different microorganisms. Right? So let's take a look. What are these? Is the sound okay? So in wastewater, composition is very complicated, right? So the video was talking about a few characteristic microorganisms you can use to judge the treatment efficiency, right, etc. And it has so many concepts in that video, but we are going to learn them all. Okay, FM ratio, mixed liquor, etc. Okay, in our class. Right. So what do we do here for wastewater treatment course on this wastewater treatment part? Right. We can learn a lot of things. We can study the composition of this microorganism. We can study the process parameters. Right. We can study a certain portion of the organics. Right. For example, trace micropollutant. Right. Very low concentration but very toxic. Right. So a lot of things. But in our course, we are going to focus on modeling, process modeling. Right. How we understand the process by establishing a model. Okay, by establishing a model. And very important part of that model is the growth of microorganism. Right. So during their growth is the consumption of organics. Right. So they consume organics to grow. So we need to describe their growth. And then we know how much they consume. Right. How much they consume is how well you treat the water. Does that make sense? Yes or no? That is the fundamental mechanism we are utilizing. Right. The microorganisms eat the organics. By describing their growth, we could describe their consumption of organics. Okay, organics. So the first thing we study is growth kinetics. Now we are moving to some math, but not very complicated math. Okay, but you have to spend some time to understand what we are doing here. Okay, all this mass balance, etc. In this lecture, during class, unless you have learned this, okay, you may get confused because we have so many terms and we put them together and we have a governing equation and we try to solve certain part, right? It appears somehow difficult. After class, you must go through all the slides to understand that. Okay. Right. So how we describe the growth of microorganism as well as their consumption of substrate. The substrate here means organic. Okay, organic. So on the left hand side, what is that? S is substrate. ds over dt. What is that? Change of substrate, change of organics concentration, right? With time. ds over dt. Right? ds over dt. What does minus mean? You have a minus sign because you have substrate concentration decreasing. So ds over dt is elective, right? Elective. You put a minus sign. On the left hand side, you have positive term. Positive term. On the right hand side, it connects consumption of substrate with microorganism concentration. Okay, so this part is consumption by microorganism. What is x? X is microorganism concentration. Okay, so the consumption is proportional to the microorganism concentration. The more microorganism, the more consumption, right? Here. And K is maximum rate of substrate consumption. So it's a rate constant. It's a rate constant. And S is substrate. Okay, S is a substrate. So we could look at this term, S over Ks plus S. Okay, so that describes the consumption of substrate under different substrate condition. You could have a lot of food, you could have very little food, right? Under different conditions, the consumption is different. So this term is to describe different condition. Okay, so Ks is half velocity coefficient. Half velocity coefficient. It's also a coefficient. Right? And this equation is empirical. It's very similar to the mechanics-Manton equation. And this equation is enzyme kinetics. Okay, enzyme kinetics. These two are very similar because utilization of substrates by microorganism is also catalyzed by enzymes. Okay, so it's also catalyzed by enzymes. So these two share the same form. Okay, minus ds over dt equals k times x times s over ks plus s. That is the consumption. So how we understand this equation? Let's change this a little bit. We divide both sides with x, and on the left side we have minus ds over dt divided by x. This is specific rate of substrate utilization. What does specific rate mean? Specific means this number is divided by x, divided by the microorganism concentration, right? So that is per concentration. Okay. If we plot this, we get this curve. Right? This is the equation. You could find specific rate of substrate utilization is a function of S, is a function of total concentration of substrate. So how much substrate you have? If you have a lot of substrate, the utilization rate will be K. K is the maximum. Right? K is the maximum. So you can imagine that if you have abundant food, the microorganism will eat as fast as they can. They will eat at the maximum rate. Right? So when substrate is large, S is large. Right? And right? So when S is small, you have little food, they grow at the rate K over Ks. K over Ks. Right? So we look at this way. When S is very small, look at this equation. So S is much smaller than Ks. And you get So the denominator is just Ks, right? So the rate is K over Ks. But if you have a lot of food, S is much larger than Ks, the denominator is just S. So it grows at a rate of K. K is the maximum rate. Okay? It appears to me everyone is confused now. But anyway, let us remember this equation for now. We're going to utilize this again when we develop the model. Okay, but this equation is simply relate consumption of organics with the growth of microorganism. We look at it, X. The X is the microorganism concentration. Right. This is a typical wastewater treatment process. I believe it has been introduced to you in our last lecture, right? So we'll skip all this: gradient removal, primary sedimentation, secondary sedimentation, disinfection. Right, this is disinfection. All the fundamental principles we have learned in our water treatment part. Okay, so we're not going to repeat them again. It's the same. What we focus will be here: biological treatment, biological treatment. And you see, we need electron acceptor. Okay, air or pure oxygen. Right, so air contains 21% oxygen. We'll focus on this part, but later we'll talk about sludge treatment. Okay, sludge treatment. The essence of wastewater treatment is biological oxidation. Right, the purpose is removal BOD, biological or biochemical oxygen demand. Right, that is carbon. Right, carbon or organics that can be consumed by microorganisms. Right, and we discussed two types. The first one is suspended growth treatment scheme. The most common we say is active sludge. Okay, active sludge, like in Shati and switch treatment works, we have active sludge process. So what does suspended growth treatment scheme mean? The microorganisms are suspended in water. Okay, so they have this kind of what we call granule. Okay, granule, it's like a particle, right? Large particle. You have your microorganism and other substances, and in wastewater they're suspended because we have aeration. They're agitated. Okay, so they do not settle. Most common active sludge, and we have a second type, which is called attached growth treatment scheme. So literally, the microorganisms are attached to a certain surface. Okay, we also call this biofilm treatment process because when they attach, they develop biofilm. Okay, so this is fixed film system, and the typical is trickling filter. Therefore, in wastewater biological treatment, we have two main categories: suspended and growth. Suspended growth treatment scheme and attached growth treatment scheme. Right. So in today's lecture, we focus on active sludge. In next lecture, we will spend probably half in talking about attached growth treatment scheme. Okay. So the most common you will see will be suspended growth treatment scheme, like active sludge, almost everywhere. Okay. So both processes are aerobic, oxygen involved, because oxygen will serve as the electron acceptor. Okay, electron acceptor. Wastewater organics serves as the electron donor. Therefore, you have electron donor, you have electron acceptor. There'll be oxidation and reduction reactions. Okay. Wastewater organics are degraded. Therefore, BOD is removed. Let's take a break. Okay, let's take a break. If you have not submitted homework, please put it here. All right. Okay, let's continue. So as I said, wastewater organics are converted into CO2, right? So that is part of the utilization. And when you convert wastewater organics into CO2, in the process, what do you get? What else you get? What else you get? Energy, right? So wastewater organics, CO2, that's oxidation. When you calculate the reaction from a thermodynamics perspective, right, which we will not, but in my undergraduate class, I use last students to calculate thermodynamics. So that produces energy, okay? Because when microorganisms grow, they need energy to grow, just like all of us, right? When you want to grow, you need energy, and that energy comes from food, right? Your consumption of food. So that's the same for microorganisms. And so to be more specific, for utilization of wastewater organics, C10H19O3 nitrogen, that is a representative chemical formula for wastewater organics. Right? So one part will be converted into CO2, water, and other chemicals, and that process is called respiration. Okay? Respiration produces energy. Okay, so what is the energy used for? For the synthesis of cells. So microorganism could reproduce and multiply. Okay, multiply. And the total fraction, the combined for the two parts is 1, right? The fraction used for energy production, the other fraction used for cell synthesis. And this is cells. Last lecture you have calculated theoretical COD of cells. Anyone still remembers the number? Theoretical COD of cells. What is a cell? C5H7NO2, right? We use this chemical formula to represent cells. Bacteria cells. What is theoretical COD? You haven't calculated. So how we calculate theoretical COD? How we do that? C5H7O2, then what is COD? What is COD? Oxygen, right? And then CO2 and water. Then you balance the equation. Why no? You balance the equation, then you calculate theoretical oxygen demand. And what is that? What's the number? Of course, nitrogen here you get NH3, right? Not NO3. What's the number? Theoretical chemical oxygen demand of cell? No one remembers. 1.42. What is the unit? What is the unit of COD? Gram oxygen per gram cells, right? Theoretical COD of cells. Of course, you have to balance the equation first. So this is 5, and this is 1. What is this? Is 2, right? And what is this? So in total, you have 10, 12 minus. This is 5. Okay, 1.42. How we get 1.42? How we get 1.42? 5 times 32 over. What is this? Say 5H3, 113. Okay, so you get 1.42. Theoretical COD. Okay, so this is just a review, last lecture. Okay, last lecture. But we use this kind of co-formula to represent cells. Okay, so wastewater organics, because cells, you see, cells you have carbon, right? You need carbon. So this carbon comes from organics, right? So for human being, if you want to grow, you also need carbon, right? So where does our carbon come from? From the rice you eat, from the noodles you eat, from the Coke you drink, right? The milk, the protein, etc. Okay. The two fraction for cell synthesis, the fraction for energy production, right? And typical value for cell synthesis, 40%, 0.4. Okay. For energy production, 60%, 0.6. 0.6. But these values depend on the nature of the waste and how long the residence time in the treatment system. Right? Right. Right. So the philosophy here is we have wastewater organics, right? They are contaminants. They are not desirable. We utilize microorganisms to degrade them. One portion has been degraded into CO2 and water that produces energy, and one portion is converted into cells, new cells, right? New cells. Does that make sense? And the cells is COD. Cells is COD, right? Therefore, we cannot directly discharge the cells into our environment, right? Our environment. So we need to remove the cells before they are being discharged into our environment. Okay? What do we do? What do we do? We have this secondary clarifier. Okay? In water treatment plant or water treatment process, do we say secondary sedimentation? Do we say that? Yes or no? No, right? What do we have typically? Coagulation, fluctuation, sedimentation time, right? Then standard filtration, and then disinfection, right? So that's the most common process, but we did not say secondary clarifier. But in wastewater treatment plant, because we have biological process here, right? Biological process, and we can have secondary clarifier. So the main purpose for secondary clarifiers is to remove the newly grown cells, right? Imagine you have this aeration tank. You have wastewater come in all the time, right? If there is no waste or no removal of cells, the cell concentration will continue to increase because you are supplying continuously food, right? The microorganism will grow forever. Of course, here we do not talk about the limitation of the tank. Therefore, we have to remove them. We need to maintain a constant concentration in this aeration tank. Okay. Secondary clarifier is to remove the extra cells. Okay, extra cells. Right. So the essence of this part is to model the biological process. These tanks. Okay, these tanks. It's very similar to what we have done for all the tanks before, sedimentation tank, etc. How we size the tank, how we determine the size. But here it's the same. How we determine the size of the aeration tank. Okay, how we determine the size. It's a little bit more complicated because here it involves the microbial process, right? We need to describe this microbial process to get a better modeling of the biological treatment. Right? So we move to this concept, process modeling. Okay, process modeling. But we are doing the simplest version of all. Okay, the modeling could become very complicated if you do not satisfy certain assumption, right? Assumption. So why we do this? We have a few objectives. The first objective is understand the effluent quality, right? So that's very straightforward. You have a wastewater, you design certain tank, right? You want to know whether it works for your standard. You have to calculate the effluent quality. That's our first goal, right? The second goal, design a process. You have wastewater, you have this effluent quality standard. You need your wastewater, treated wastewater to meet this standard. You need to design this tank, right? Design this treatment process. So design the treatment process, and then talk about sludge, right? Sludge. So here we have much more sludge produced than water treatment process. In water treatment process, for example, sedimentation, right? At the bottom, you will collect a certain amount of sludge. Do you still remember one problem in class exercise? When you add aluminum as coagulant, how much sludge will be produced, right? But here you have a lot more sludge. And the sludge is mainly composed of cells, right? The newly grown cells. And the treatment is expensive. Treatment sludge is expensive. Okay? And we utilize anaerobic treatment, which we'll talk about, we'll cover in our 10th or 11th or 12th lecture. But we'll talk about that. And all predict organism concentration needed in the treatment system, right? So we start with this equation. Microbial growth minus ds over dt equals kxs over ks plus s, right? So someone asked me during the break, what is ks? Ks is not a coefficient. Ks, if you go back to read the slide, right? Ks is a concentration. And what concentration? Ks is a concentration when one condition meets. What is the condition? ds over dt divided by x. So this is specific rate of utilization of substrate equals k divided by 2. K is the maximum, so half maximum. Okay, when the utilization rate is half the maximum, the concentration is Ks. So Ks is a concentration. Okay, Ks is a concentration. After class, please go to that slide. Okay, carefully check what is the definition. But Ks is a concentration. Ks is not a coefficient. Okay, but anyway, we started with this. X is cell concentration. It's variable in this equation. So what we would like to develop is an equation to describe the kinetics of micro growth. So what we want to know dx over dt. X is microorganism. Dx over dt is change of microorganism concentration with time. Right. Let me make sure everyone knows this, right? What is dx over dt? You learn a certain calculus? No? How we get dx over dt? What is, so do you know delta x over delta t, right? So what is delta? xt minus x mean x0, right? T minus t0, right? So when t is very small, right? When you look at a very small scale, this is dx over dt, right? So that's the definition of calculus. Okay, just make sure everyone knows what we are doing here. dx over dt, that's a change of x over t, right? Change of microorganism concentration with time. We want to describe this. So with formula C5H7O2, so carbon needed, nitrogen also needed, but some other micronutrients like phosphorus and sulfur and iron, etc. also needed for the microorganism to grow. Right? In most of municipal wastewater, carbon is a limiting nutrient because we need a lot of carbon. Right? There isn't enough nitrogen, phosphorus, and sulfur. Right? Carbon is needed for cell synthesis and needed for energy production, as we mentioned earlier. And this one, this is bacterial growth with time. Right? So for cell growth, there are multiple stages. multiple stage. At the very beginning, it's very slow, and then it accelerates, right, very fast, and then stable stage, and then decay. The y-axis is the mass of organism. Okay, x-axis is time. This is cell growth, different stages, and corresponding to the utilization of substrate. So you see here the substrate concentration decreases, the cell concentration increases. Right, and we began to encounter many concepts. Okay, many concepts. These concepts are what you need to manage. Okay, yield. What is yield? Milligram cells formed over milligram organics consumed. Right. So how many cells over how many food? Right. That is yield. Okay, this is a very simple concept. Say 1 gram substrate is consumed, 0.6 gram cells is produced. What is the yield? What is the yield? 0.6, right? 0.6. So the yield, it has a unit, 0.6 gram cells per gram substrate. Okay, pay attention to its unit. But the number is 0.6. Okay, so the yield definition is very simple. And yield is a function of the substrate and the electron acceptor. Okay, electron acceptor. We have one example, glucose oxidation. This is thermodynamics. Delta G is active, so the reaction produces energy. And so for cell synthesis, it consumes 145 kilocalorie per mole glucose, right? 1 glucose, 1 mole produces this much energy. And for cell synthesis, it consumes only this. Right? So how many moles of cells can be synthesized by utilizing 1 mole of glucose? This number, right? 688 over 145. 47 moles. Right? From an energy balance perspective. Right? The ratio is more like 3 in reality. And then the yield is not 3, right? Because 3 is 3 moles of glucose to cells over 1 mole of glucose to energy. You still need 1 mole glucose to produce energy. So total glucose will be 4. Okay, so the yield will be 0.75. 0.75. Okay. And now is the definition of yield. Why we need to define yield in our process? Why? Because of this, right? Yield connects the consumption of substrate and the growth of cells. Because that's our definition. So tell me, what is yield? What is Y? What is Y? What is Y? Cells grow over substrate consumption, right? Cells grow, if we use mathematical term, it's dx over dt, right? What is the consumption of substrate? Consumption of substrate is minus ds over dt, right? The minus sign because it's negative. This part is negative. So this is yield. It's from its definition. Do you want me to? Okay. So this is the definition of yield. And this will be useful. This will be useful. And what we get? We get the first term. Remember, we want to write an equation on cells in the tank, microorganism in the treatment tank. So this term is to describe the growth of cells, right? The growth of cells in the tank. dx over dt equals y times minus ds over dt. So this term is growth. And then next we consider the death of cells. Imagine in the aeration tank, you're supplying food, so the cells are growing, but some cells are dying, right? Some cells are dying. So we use a term to describe cell death rate. It's just minus b times x. So this is first order reaction kinetics. Minus because of reduction. Okay? B is a rate constant. B is a rate constant. And we call B the decay coefficient. Okay, decay coefficient. Decay coefficient. And its unit is 1 over day. Okay, per day. So the death is minus bx. And the net growth is the growth minus death. Make sense? Okay. So far so good. So far so good. Okay, so for this equation, is there anyone confused? Oh, everyone is confused. dx over dt. All right. So what is ds over dt? Very early we learned this. Right? At the beginning of today's lecture, we have this from the growth kinetics, microbial kinetics. And we plug in this term into this equation, we get this. We get this. Okay, we get this. And we transform this a little bit. We move x to the left-hand side, we get this. This term. Okay, this term. And then we have today's second important concept. The first one is yield. The second is net specific growth rate, mu. And we define mu this term. Okay. So the first important, this is yield. The second concept, specific net growth rate. Okay, specific net growth rate, or net specific growth rate is this term. Y times K times S over Ks plus S minus B. What is net specific growth rate? What does net mean? It's growth minus death, so that's net, right? What does specific mean? Specific means dx over dt divided by x. X is specific, so it's a fraction, right? It's change over total number. So it's a fraction. It's a fraction equals this. Okay, net growth rate. It's still a growth rate. Okay, therefore, when we look at this, there is a maximum mu. Maximum mu when S is very large. Right? When S is very large. What does S very large S mean? What is S? Substrate, right? It means a lot of food, a lot of substrate for microorganisms. Therefore, they will grow at the maximum rate, right? When S is much larger than Ks, so this part is S, right? This part is S because S is much larger than Ks. So Ks is a concentration. Ks is a concentration. S is much larger than Ks. You have S here, and then you can cancel S. It's Yk minus B. So that is the maximum rate, growth rate. When you have a lot of food, the microorganism grow at a rate of Y times K minus B. Okay, so that is the net rate, maximum. Okay. All right. Let's still do a few minutes. Right. So all these are the basics. Later we are going to use for the modeling. So we're going to put all these terms together. We write an equation and we'll try to solve some useful terms. But before we do that, let's introduce different variations of active sludge. Okay, so active sludge is one of the suspended growth rate scheme, right? So active sludge microorganisms are suspended in the tank in water, and so depends on the tank. We have different variations. For example, this is plug flow, and this is step variation of plug flow. So here you introduce influent at different locations along the tank. Okay, and for this one you introduce at the very front, right? And this one is completely mixed, so the tank is well mixed. And this one you have circulation. We call this oxidation ditch in the tank. And this one XPR. XPR is not a continuous flow. Other treatment scheme is continuous flow. So you have a constant Q flow rate. But this one is a batch. You have only one tank, right? Fill, react, settle, decant. Okay. At different time, by single tank. And this one is multiple well mixed tank in series. Still the continuous flow. And this one you have two tanks. One is contact tank, and the other is stabilization tank. And this one you have a selector. Okay. We will introduce more details regarding the variations of these tanks. The most common you will see complete mixed reactor and plug flow reactor. Okay, these two are the most common ones. What is aeration tank? We have aeration, right? So we have here gas diffusers at the bottom. Many diffusers, right? You can pump in air. In certain cases, you can pump in oxygen, pure oxygen. Okay, pure oxygen. So they are supplying oxygen. Oxygen is the electron acceptor, right? As we said, we need oxygen to have the redox reactions. But also we are doing agitation. So these microorganisms are suspended. Okay, are suspended and mixed. And we use pump. Therefore, because we are pumping, wastewater treatment is energy intensive, right? Energy intensive. And also from the earlier video we watched, biological treatment process is to intensify the natural process. Right? You say all the microorganisms are natural. Imagine there is a river or there is sea. We discharge a limited amount of organics into this water. It's completely fine, right? Because we have microorganisms there, they can degrade this organics, right? But for our wastewater, the concentration is so high, we cannot do that. And what do we do? In this tank, we intensify the process, right? Intensify the process. And what's the intensification? We have very high concentration of microorganism. Okay. In natural environment, you may have only a few milligram per liter microorganism, but here it's thousands of times higher, right? You could have 3,000, 4,000. In MBR, you could have 10,000 milligram per liter. So the concentration is very high. You have so many microorganisms here, and all of them, right? You consider the population. You need a lot of organics. You need a lot of oxygen. So it's an intensification process. Intensification. Okay. Before we take a break, I'd like to ask any question. No? Okay, so let's take a break. If you do not understand some of the parts, you can ask me, or you can go back to the slides. For this part, you have to spend some time. right? Okay. As I mentioned earlier, we intensify the process, right? We aim to have a very high concentration of microorganisms in the aeration tank. How can we achieve that? How can we achieve that? Very high concentration of microorganisms in the tank. More S, more food. Okay, but typically your food is fixed. It depends on the wastewater. Right? So a smarter way we utilize is recycle of cells. Right? When you look at wastewater treatment process, this is aeration tank, this is secondary clarifier. Right? A very distinctive feature is you have a recycle flow. What is the purpose of secondary clarifier? To separate cells, right? The cells settle at its bottom. So here you have very high concentration of microorganisms, right? And a portion will be recycled into the aeration tank. Another portion will be wasted. Right? So that's recycle flow. Recycle back to aeration tank. Okay, that's a way we utilize to maintain a very high concentration of cells. Right? Why we do this? Because we want to control the cell residence time separately. What is residence time? What is residence time? What is HRT? Tell me, what is HRT? So almost every class I ask you the same question. What is HRT? So how long the water stays in the tank, right? It is V divided by Q, right? V divided by Q. If we do not have this recycle flow, the cells go with the water, right? So they stay in the treatment system for time of T, for time of HRT, right? For time of HRT, so you cannot control. But if you have a recycle flow, you can separate the cell resistance time with hydraulic retention time. Okay, because here you recycle a portion of the cells back into the tank, therefore they stay in the tank longer, right? Virtually they stay in the tank longer because they go back, right? So here we have another important definition is cell resistance time, theta C. Okay, it has a lot of name: cell residence time, or solid retention time, etc. But it's the same. Okay, theta C. Subscript C, cell. Okay, HRT, now we call it theta. Okay, it's theta, which is hydraulic retention time. Theta is HRT. Theta C is cell residence time. Okay. Cell residence time is not hydraulic retention time because we intentionally separate these two, right? We want theta C to be much larger than theta. Theta C much larger than theta because you want a high concentration of cells, right? The theta is always V divided by Q, hydraulic retention time. Okay, theta. Theta C is different. We will define theta C, how to calculate theta C later stage. Okay. So you should know theta C is not theta. Theta C is actually much larger than theta C. Or theta C is much larger than theta. Okay. Cell residence time versus hydraulic residence time. Some parameter. Let's see. Let me skip this. The detailed process, what happens? So typically, say in the tank, right? So we define X. X is volatile suspended solids. Right? So it's an approximation. What is a volatile suspended solids? Volatile. What is volatile? What is suspended solid? What is volatile? What is suspended solid? So go back to your slides, okay? But here we use VSS, volatile suspended solid concentration, to represent cell concentration. Although we know that volatile suspended solids are not completely cells, right? You could have other substances, but for engineering convenience, we just use VSS concentration to represent X, microorganism concentration. Right? VSS concentration in the aeration tank is about 3,000. It's very high, 3,000. Okay, we have some microorganism concentration in the influent. It's about 125. Okay, to the aeration tank is about 50 to 60. Comparatively speaking, this is very small. 50 versus 3,000, right? 50 versus 3,000. This is almost zero. Microorganism concentration in the influent, X in, is almost zero. So that is one assumption we make. Okay, X in is zero. And here we only solve the equation when X in is zero. But in your textbook, okay, X in, there is one scenario X in is not zero, which is more complicated. Okay, but in our class, we only discuss X in is zero. But if you're interested in learning more, just go to the textbook. Okay, I'll solve the equation when X in is not zero. Okay, we directly come here. We discuss the modeling. Okay, so here we have the process train. This is aeration tank. This is secondary clarifier, right? And we have all this number. We have Q, flow rate, into the aeration tank, and the substrate is S0. Okay, initial S, And we have this tank. In the tank, the tank volume is V. Microorganism concentration is XV. Okay, XV. We have oxygen in, right? And we have this recycle flow from second classifier. Therefore, what is the flow rate out of the aeration tank? It should be Q here minus plus QR, right? Because you have a recycle flow. Both in, this is out. So the outflow should be Q plus QR because of recycle. Yes or no? Yes or no? Okay, the outflow substrate concentration is S because of microbial utilization in the aeration tank. The substrate concentration changes or decreases, right? Decreases to S. And then the flow goes into the secondary classifier, right? And the outflow will be Q minus QW because here you have Q plus QR in, you have QR out and QW out. This is recycle, this is waste, right? So the outflow will be Q plus QR minus QW. Therefore, it's Q minus QW. Okay, and the cell concentration is XE because here it's XV, right? Because this is complete mixed tank. The outflow has the same microbial concentration as the tank. So this is XV, but it's a second clarifier, it's clarification. And at the bottom, we get a very high concentration, which is XR. In a supernatant, we have XE, right? XE. That is a function of second clarifier to separate cells from the effluent. Okay, from the effluent. Just to give you a sense, XV into the second clarifier, 2,000 to 4,000 milligram per liter, right? XR after clarification or settle, XR could be 10,000, 12,000. So it's very high, concentrated. XE will be very small. XE maybe 10, 50 milligram per liter. Okay. Right. So we do the process modeling, but here we consider aeration tank and clarifier together. Okay, together. So we do process modeling based on this red box. Okay, red box. Right. So this is in, this is out, this is out. Right. At current stage, we do not consider the recycle. That's internal. We just consider here. This is in, this is out, this is out. Make sense? Right? Because that's process flow. Question? Question? Okay, we do not consider internal flow, which is recycle. Just only in, out, out. Okay, we're going to write expressions for all this. Okay, for all this. So we start with some assumption. This is a CSTR. So the tank, aeration tank is well mixed. So you have a uniform XV in the tank, uniform S in the tank. And ignore active biomass in clarifier. So there is no microbial growth in the clarifier, only in the aeration tank. Always the stabilization occurs in the reactor, in the aeration tank. No VSS in influent, which is X in is 0. Right, X in is 0. Okay, so this equation is the most important. Mass balance on X. Mass balance on X. We're talking about here. The change of microbial concentration in the system. The system means this red box. Okay, red box. Right? The change of microbial concentration times V, that's mass over time. Mass over time equals the growth and the transport term. Right? Transport term, removal. Removal term. Right? So that is the mass balance. This is reaction, this is transport. Okay. So we plug in all these terms. Growth is this one. I hope you still remember growth minus decay. Right? So in the aeration tank, microorganisms growth, but also the die. So this is the net. This is the net. Right? How about transport term? Transport term, what's come in? What is the amount of come in? Q times what? Q times what? We're talking about microorganism. Q is the flow rate. So the in term, Q times Q is flow, right? Times concentration. What concentration? It's X what? X what? X in, right? X in. Right? So here. So this is X in. That is how much microorganism going into the system, going into the red box. Right? Q times X in. Flow rate times concentration. What is X in? What is X in? Here. 0, right? 0 is our assumption because X in is very small. So this is 0. Right? This is 0. In our case, in your textbook, it could not be 0 because the equation becomes more complicated. You can go to read the textbook. So this is 0. How about out? Look at this. How about out? What is out? So we have two flows. Outflow, right? This one, what is the mass? QW times XR, QW times XR. What is the other? Q minus QW times XE, right? Times XE. So this is in, this is out. The difference is the transport term. Right? So let's come back here. Physical removal. Right? So here it's 0 minus this term. Okay? We did not write 0 there. But in is 0. Okay? This is just the out term. Right? So the entire equation will be looked at this. This is the net growth. This is the transport. Right? So actually here should be plus 0 minus this term. We just omitted 0, the in term. Okay? This one is fine. Question? What are we doing here? We are describing the change of x. We are describing the change of x in this red box. Right? In this red box. These equations are based on our assumption. We have made some assumptions. For example, we say that microorganisms only grow in this tank, not in a secondary clarifier. Okay? That is one of our assumptions. We assume x in is 0. Okay? That is also our assumption. Okay? Therefore, we could get, this is the mass balance equation, and we write it in the mathematical form. It will be like this. Okay? This is the mass balance. This is the mass balance. So everything we did is to reach this step. Everything we have discussed, the purpose is to reach this step. Right? We have discussed every term of this equation. Okay? Any question? No, right? All right. So next is steady state. What does steady state mean? The treatment is in steady state. So XV does not change with time. Right? So you have a constant concentration, for example, 3,000, 4,000 in the aeration time for the microorganism. Make sense? Right? In practice, during the operation, microorganism concentration is the same. So XV is a fixed number. What does that mean? dx over dt is 0 because the change is 0, right? So the derivative is 0. dxv over dt is 0 because of steady state. Okay, so the left-hand side is 0. Here is 0. And we rearrange this equation and we divide both sides by xv times v. And we get this. We get this. What is the left-hand side? 30 minutes ago, we just defined. What's the left-hand side? Mu, right? It's mu. What is mu? This is mu. What is mu? Net specific growth rate, right? So this is mu. Okay, so this is net specific growth rate. Left-hand side is mu. Okay, this is mu. And mu equals this term. Okay, we are going to define the right-hand side. So what's the right-hand side? Here we define theta C. What is theta C? Cell resistance time, right? Cell resistance time, how long cells stay in the system, right? How long cells in the system? What is the concept? Actually, it's mass of VSS in the system over the rate of removal, right? Rate of removal. Imagine the concept of hydraulic retention time. How long water stays in the tank? We say it's V divided by Q, right? It's volume. But if we times both with the what? Density. What is that? It's mass, right? It's mass of water in the tank divided the removal rate water, mass rate. So it's the same here. Theta C, mass of cells in the system divided by removal mass rate, right? So that's cell residence time. It's the same like hydraulic or water residence time. Okay, therefore theta C is xv times v divided by removal. This is removal, 2 streams. Okay, 2 streams. What do we get? We get here 1 over theta C equals mu. 1 over theta C equals mu. Right? This is a very important equation. 1 over theta C equals mu. What is the physical meaning of this equation? Equal 1. Equal, what does equal 1 mean? What's the physical meaning? So 1 over theta C equals mu. Right? For this equation, what does this mean? I mean, this is the mathematical form, but physically, what is theta C? How long the cells stay in the tank, right? What is mu? How fast they grow, right? How fast they grow. Mu, net specific growth rate, right? So in practice, we change theta C. we change how long the cells stay in the tank. They will change accordingly how fast they grow. So this is the engineering way for us to control the wastewater treatment process, right? Also look at this equation. Look at for specific wastewater like Y, K, Ks, and B decay coefficient are determined. So the effluent quality depends only on theta C. Depends only on theta C. What does that mean? What does that mean? If you have wastewater, right? You have a wastewater which needs treatment. You want to achieve certain effluent quality, which is S. What do as an engineer? You change theta C. You change theta C. You change how long the cells stay in the tank. You will achieve desired effluent quality. Okay. So generally speaking, if you want to achieve lower S, you need larger theta C. So you want the cells stay in the system longer. Okay, longer. And that is from the process modeling. And that is what we do in reality to control the treatment process, right? How you get different effluent quality. You change theta C. And later we'll see how we change theta C. Okay. Any question? I know there are too many concepts. But you should not be daunted by this equation. It's not hard. Right? Although you say dx over dt, but we'll never use the calculus, right? It's very simple math. It's very simple math. Okay. In the exam, all these expressions will be given in the appendix. Okay. You don't have to remember, but you have to understand. This is mu and theta C. All right, we have another concept or definition. This is our definition of theta C, right? We have not. Okay. XE is generally very small. XE, effluent, right? We have very few cells. XE is very small. When we neglect this term, we have this term, right? For given reactor volume and design XV, theta C is controlled by varying QW. Okay, QW. So what do we do? We change the volume of the waste stream. How much you waste? You change theta C. Right? So QW is a very convenient parameter for us to control in wastewater treatment. The waste here, the waste flow stream, this one. Okay, so we change QW, we change theta C, and we change S. Okay. So all this is based on this modeling, process modeling. So we learn how the process is operated, how each variable, how each parameter is connected with each other, and how we can control parameter to realize the control of the entire process. Okay, and if you change theta C, you change mu. As we said, 1 over theta C is mu, right? So mu, the microorganism self-adapt. So that is the amazing part of wastewater treatment. Right? Okay. This is the first very important expression. And then we define U, utilization, specific utilization rate. It equals mass BOD removal over time over mass of cells present. Right? It's just like this. It's actually K times S over Ks plus S. Therefore, 1 over theta C equals 1 times U minus B. Right? U. Why we do this? Why we do this? Why we connect this with U? Because we have another expression for U. Right? So U could be this. What is U? Mass of substrate over mass of cells. Q times S, 0 minus S. Mass of substrate consumed. Right? XV times V, mass of cells. So U has another expression. Okay? And when we look at this, when we think S is very small, we get this food to microorganism ratio. This is another important concept. F to M ratio. F to M ratio. Right. This is very convenient to use in engineering. Okay. In many design, you will use this parameter, FM ratio. Okay, FM ratio. Food, substrate, in the influent, right? Microorganism, XV times V. Food to microorganism ratio. It's a rational design parameter. In design, right, you may use this parameter. Right. So from this equation, we can solve S, effluent quality. Right. You should still remember our goal. of this process modeling, why we do this complicated modeling. In reality, it's not very complicated. Okay? The complicated cases are in the textbook. So here we're discussing the simplest version. Right? We want to design the tank, or we want to know the effluent quality. So this is S. S is a function of theta C. Okay. And then we replace U with Q times S0 minus S divided by XV times V. We could solve XV. XV is cell concentration, microorganism concentration in the tank. Right? So this is also the parameter we are interested in, XV. So now we have S, we have XV. So eventually we get this XV. Mu max. Right? So earlier we said that the maximum mu will be YK minus B, right? YK minus B when S is much larger than KS. Right? But here for our wastewater treatment, S is not a random number. The maximum S will be S0, substrate concentration in the influent. That is the maximum S we can get. Right? So here the maximum mu will be this term. Okay? It's not Y times K minus B. So this is mu max, because mu is 1 over theta C. When there is a mu max, there is a theta C minimum. Theta C minimum. The wastewater treatment plant should operate with a theta larger than theta C minimum. Otherwise, what we call washout will happen. Okay, washout will happen. What is washout? What is washout? Washout, the cells cannot grow as fast as the waste, right? So you waste too much. You waste the cells too much; they cannot grow that fast. So that is washout, in simple language. In design, we apply a safety factor. Theta C design is safety factor times theta C minimum. And safety factor is between 20 and 60. So what's the time? So everyone's still okay? I think I probably should stop here because I will have a little more. We can leave to next. Okay. But what you will need to do after class, you have to go back to the very early slide, starting with the microbial growth kinetics, right? Minus ds over dt equals k times x times s over ks plus s. From there, okay, step by step to the mass balance equation. Okay, mass balance equation. This is not very difficult after you manage the process, understand all the concepts. Okay. Although it could be the most difficult part in this class so far. Okay, so far. But this is engineering. This is engineering. So you say that we're trying to model the process, right? We conceptualize the treatment. You are using math to describe the whole process and try to understand what's happening quantitatively in the process. So that's very important mindset, engineering mindset. All right, not yet. Okay, not yet. Please be seated. All right. So definitely will be covered in the exam. But all the expressions will be given to you in the appendix to the exam paper. But you have to understand all these expressions so that you can use them. Otherwise, you cannot. Okay. All right. So in the next lecture, we have some practice problems. But be prepared, okay, when you come next lecture. Otherwise, you'll be still confused. You have to prepare for next lecture and try all these in-class practice problems next lecture. So you have to review all the notes, derive the equation by yourself step by step. Although I will not ask you to do that in exam, in the homework, but you have to know how to use all these expressions. You have to do that to understand the expressions, otherwise you cannot use. That's very important. Okay, do that before you come to this class next week. Otherwise, you don't have to come because it will be the same. You come or not come. Okay? Okay? All right, homework, last call. All right? See you next week.